Hi everyone. Emre, I would like to say thank you for the intro. Okay. As we all know, we have taken a lecture on graph last time, and we have learned one algorithm. It's called Bfs, and I would like to start by talking about it, and I would like to have one individual volunteering to answer about it, or in short, to describe about it. What is Bfs? Looks like we need some monitoring on the last lecture. Okay, I'll start. As the name implies, depth first search. We'll traverse the graph as we have a depth, meaning as we have a node or a vertex that is not now, we'll go that way until we find there is nothing to go, and we'll backtrack. And thanks to Kudus, I think we have seen a good example. Yeah. And today we are going to cover another type of traversal, which is rate first search. And for this slide, I would like you to closely see the difference between two traversals. It might be difficult for you to understand while seeing both of them. Try to see one and the next time. What's the difference?
The first one just fills the depth first, then the other one fills by the width. It's called horizontally. This one goes vertically first.
Yeah, you're correct. The first one, as we see, it will start from the root and go up until it finds nothing, meaning it will search for the depth and it will backtrack. Do the same thing for the all possibilities. The other one will go level by level. First the root, then the second level, the third level, and the last level. Simply, that is Bfs. It will go level by level. That's the key property of Bfs. As we define Bfs, we will define Bfs, and as we have seen on the visualization, Bfs explores all of the neighbors nodes at the current depth before moving to next steps. So it will finish all nodes or all the vertex that are on the given level, then it will go to the next level. If you remember, we used one data structure on DFS. Can someone guess? Assuming we don't use recursive. Actually, yeah, it can be recursive, but that is one data structure we use.
Graph?
Not stack. And based on this, can someone guess what type of data structure are we going to use on DFS? Q. We are going to use Q on BFS. Why Q though? Why would we use stack? There is a reason behind it. The reason is, since BFS traverses level by level, we don't know if we use stack how many levels. Actually, we can do that, but it would be inefficient. And Q, by definition of Q, it will directly give us the level by level traversal. The first node that enters the queue will be the first one to be held or removed. So it will be inserted, and the next level will be inserted, and then. Okay. Let me draw the graph for the trick and simulate the process. Can someone help me?
1, 2, 3, 4.
Okay. As we have discussed, we are going to use a cube. So let's try to simulate it. We have a cube, and direction of extension is like this. What will be the first thing that will be inserted in the cube? 1. The vertex. Then we'll remove element or the first element from the queue, which is the root, and we'll print it. Let's say we are supposed to print it. What will be the next step?
Adding its children to the queue.
And
Yeah, correct. You
after that, we'll do the same thing again. We'll remove 2, which is the first of the queue. We'll print it. What's the next step?
add to string.
2 step, which is 5. Then 3 is the first, meaning the top one. We'll remove that. We'll print, and we'll add 6 and 7.
Different market.
Okay. We'll pop 4, and we'll print it here. Then we'll add 4th child, which is 8. We'll pop 5. There is 1 child, which is 9. We'll add it here. 5 is supposed to be printed here. Then 6 is the top one, or the first one. We'll hold it and print it. There is a child. We need to insert it. And then 7 is on the first one. We'll print. Since we don't have any child for 7, we don't have anything to add onto the queue. We'll move on. We'll print 8. We'll see if there is a child. No. We'll pull this one. There is a child. No. The same thing for 10. Any question how we traverse using the queue?
So since we're using a graph, how would we know how many children the current node has? So in the case of 1, we have to add all its connections. So how would we add it?
Yeah. On different questions, it depends on the question. Sometimes we'll be given references. For a tree, it might be binary tree or n-ary tree. Then we'll have a list of children, or for binary tree, we'll have left and right. Depending on the question, we'll know where to go. Just we need to understand. We will add, after calling the element, we'll add its children onto the queue. All right. Let's make one adjustment to the tree. Let's add 1 8 to this one. And we'll try to find the shortest path between 1 and 10. What is the shortest path? Meaning the number of nodes.
140.
140. Okay. If I ask you this question, what type of approach do you use?
I would say Bfs, because we're looking for the depths. So the shortest distance is going to be the one with the lowest depths. So since we're doing depths, I see Bfs.
D. Any other opinions? Let's just start the first part of the traversal and see which one gives us the shortest path. At first, what we did, we inserted the root, right? The source node. Then we'll add all of its children. Then we'll start the same process, meaning we'll hold or remove the first element, we'll add the first children. So we are going level by level. If we are going level by level, can we be sure we will find the node immediately in the shortest path? Do you get my idea? One of the key properties of Bfs is it will go level by level, as it is on the animation. We'll start from the source node. We'll go to the next level. We'll extend, we'll extend, we'll extend. And we see a destination node. can we be sure that is the shortest path?
Yeah. If we found it on an earlier level, that means that was the shortest one.
Yeah. If it is on the previous level, we'll find it when we are traversing. When we are using BFS, we'll go in the depths. Maybe there will be an edge here, and we'll find it this way, but the number of steps are too long. So when an equation that is shortest or minimum or something that is related with graph, try to think of using BFS. BFS assures us when we see a node, that is the shortest path. Okay. What is the time complexity of BFS? Not looking into the slides. What do you think it will be? Try to think of the worst case. Will it be different from BFS? In worst case, what are we going to do? We are going to discover, or we are going to reach all nodes, right? Whether we use DFS or BFS, we are going to reach every node once. So, in time complexity wise, they are the same. The time complexities of n plus n, where n is number of nodes, m is number of edges. The space complexity is the same also. We'll stop maybe in a Boolean array or hash set, some sort of that data structure that can give us constant time lookup, and we'll have at most n sized of those data types, so it will be the same. One question came to mind. Since BFS and DFS have the same time complexity, will there be a difference choosing one over the other on questions? Do you think time complexity is enough to choose approaches? Why?
Like as they've seen here, we use DFS and BFS, and BFS find the destination shorter than DFS.
Yeah. Even though they have similar type of time complexity between n plus a, that doesn't mean you have to be like free to choosing between one of them. We have to be careful on choosing. Sometimes choosing the wrong approach might lead into worse complexity or bad approach. So we have to see key points on the equation. Okay, what are the properties of BFS? As we have seen on the simulation, how many times did we discover a node? Or did we insert it into the queue? Once, right? On this case, since there is no cycle, meaning it is a tree, we are guaranteed like there is no way to go back. So we don't, in a way, we don't worry about inserting it again. But in different graphs like this, maybe I will put another, if it is directed, and let's say this one. After I reach here, I can go here. So I need to check if I already visited or not. So in that case, if we keep track of the visited nodes, we are going to add them only once. And as we discussed, it will always find the shortest path between source and destination. You can see the simulation. I don't know if it is visible, but it will start from the top corner, this, and try to reach here. And we can see that it's going like this. It is increasing level, not like trying different paths. It's increasing. So it's using BFS. It is going level by level, and it moves to the final stage. So try to visualize that when you are thinking about BFS, level by level. Okay, we'll go through when to choose. As we discussed, it's the same again, finding the shortest path or number of steps between two nodes. And sometimes we'll be asked to traverse level by level, directly or indirectly. So if there is something like that, BFS will be more appropriate. And the other thing is, if the search vertex is closer to the source node. Why? It's the same reason. By using DFS, maybe we'll choose the wrong path and we'll go long. But if you use BFS, since the destination is very close to the source node, it will give us better practical time complexity. Okay. Enough about the theories, and let's start practicing or see the example. And maybe we can show the question. The question asks us to find the minimum depth of it. Minimum depth means a path from the root to the leaf, the shortest path from the root to the leaf. And without knowing or without using BFS, how can we solve this using DFS? Any approaches?
Question before we do so. In this case, are we going to say 1 since it's 9, or is it 15 or something? When it's good to return the minimum depth.
We will return the number of nodes in the path of in the shortest path from root to leaf. The shortest path is this. So there are 2 nodes.
We add 3 to the visited node first, then we find its children and add it 9 and 20. If that node doesn't have any children, we know we have reached the minimum.
Without using
BFS, right?
Yeah, this is BFS. Without using BFS, how we can solve it?
We could do a DFS where we pass the level with the next one. And the minimum level we have to backtrack from, we take past the list.
Okay. Yeah. We can use DFS. We'll pass maybe we can start from the top or the bottom. On every node, we'll choose the minimum number of steps. And what do you think the difference is between choosing BFS and DFS on this? Do you think there will be any difference in number of function calls or number of insertions?
Because on DFS, we'll find it on the first pass, we'll just find it, but let's say we're traversing left first, and if we have the 20 on the left, we'd have to go through it first and then come back track again, so it takes more time.
Alright. Up until this point, any questions on BFS?
Can you make it more clear how do we define the shortest path? Like, what do we mean by shortest path? Can you show it on an example on this graph?
Okay. Let's assume the graph it is. The question asks us the shortest path from the root to the leaf. How many paths are there in this tree from root to leaf? 4.
3, right?
Oh.
4 is not deep, right?
Oh. There is nothing. Okay. In this case, 4, right? And this one has 4 number of nodes. This one has 4 number of nodes. This one has 3 number of nodes. This one has 2 number of nodes. And what is the shortest one? 2. And the question asks, basically this, we need to return the shortest one. Are we clear on the question? Okay.
if we tried the DFS approach, does it mean that we have to see every leaf and compare the minimum?
Yeah, if we are going to use BFS, we are going to traverse every possible, because once we reach to the leaf using DFS, we don't know if it's going to be the shortest one, so we have to look to other leaves also to make sure that we have what we have is the shortest one. Maybe we can manipulate, like we can have somewhat optimization on top of it if the number of traversal is greater than the current what we have currently. Maybe we can stop there a little tricks, but you know what I'm saying, like if you use DFS, we'll reach every possibilities.
I have one question. Okay, we understood that if we use BFS, it's gonna be more in a concise way, right? But like, how can we save the path length or something? Like right now, we can use BFS just to traverse this level by level. That's fine, you got this. But what about the paths and the lengths? How should we use BFS so that you also find the shortest path? I couldn't.
Okay. We can think of the equation like the shortest path from a root to first leaf, or to any. And if we go level by level, when we see the first leaf, we'll be sure that's the shortest one, right? You see my point?
I see.
Yeah. The key property you need to see is the level by level traversal. Okay? Because of that, that's the main reason it's giving us the shortest path. Okay, I'll start first by DFS. I'll have a helper function. We'll have a function DFS. It will accept a node. Then I'll check if it is leaf. I'll have separate function to check. I'll return 1. And I'm going to have left depth. One thing I need to see is okay, we can see here the number of nodes can be from 0 up to 10 raised to 5. So can we think what will be the maximum depth or the worst case? 10 to the 5. If it is linear, only meaning if they have only one child, and depth will be this. So thanks. I'll have max depth. Just to be sure, I will add 10. This represents 10 raised to 5 plus 10. Just to be sure. And my left depth will be, if I have node, if node was left is none, it will be max depth. Otherwise, it will be the DFS of node dot left. I'll do the same thing for right pass, for right depth. At this point I have left depths and right depths. I should just choose the minimum and add on top one on top of it. Alright. I think we are good for the BFS function. And we need also to check here if the root is null. Otherwise, I'll return BFS. Root. And there is one function remaining. At this point, I think we can check if there is any compilation error. Yeah, it's working. Yeah, we can submit it now. Yeah, we got accepted.
Can we return maximum depth if a given node is not instead of copying the terminal?
I don't get your point. Max, since we are going to return minimum depths,
Okay.
you see my point? Yeah. Any question on this approach? I think we are clear on this. We'll do this using BFS. We'll return the same thing. We'll accept the root of the tree. And first, as we discussed, we are going to use queue. In Java, there is array deq or array deq. Yeah, and the type will be, actually we need to have do we need? And we will have a loops until our queue is empty, meaning we don't have any element to process. Okay. If the queue is not empty, that means we have elements on the queue. And I can get the size of the queue. This guarantees me I'll have for loop, and this guarantees me I'll have one level traversal for that for loop only. And we'll pull the first one, and we'll check if it is leaf, this means we have reached to the first leaf based on the implementation of Bfs. And we need also to keep track of the label. At each for loop, we are going to increase the label, and we'll return the label here. If it is not leaf, meaning that has at least one child, we'll check. If the left child is not null, we'll add it to the queue. We'll do the same thing for the right child.
What if we have only one node? It should return 1 instead of 0, right?
Yeah.
Level should be start from 1, right?
Yeah. Yes.
No. Above level. Just this also. And this also works. Yeah.
This also works.
It's more confusing.
Okay. Then we'll return.
Okay. Can you explain us why it's a good idea to increase the level at the end of the form?
Okay, maybe I'll try to use this example and see what's happening in the background. To add the root. And after adding the root, we'll come here and check if the queue is not empty. Yeah, that's the element. And once we get the size, it will give us the label, the number of elements on the given level, meaning on the first level. So in this case, size is 1. So we can remove element until we reach the size and add their children to the queue. And by the time we finish iterating the size from the 0 up to size, we'll not have any element belonging to the previous level, and we'll have new elements that belong to the second level. We'll see how it. Then we'll have for loop. That will go from 0 up to size. In this case, size is 1. We'll remove. We'll add child of 1, 2, 3, and 4. On this case, we have finished the for loop. Then, what do we see here?
Please keep track of the label.
Okay. For the sake of this example, we'll start from level 1. Then we'll remove this and we'll add its children, 2, 3, and 4. And this for loop will end, meaning we have exhausted all of the previous level. And when we closely see, the elements that are on the queue are the next level elements, right? And we can increase the level here, meaning the level of elements on the queue is 2. Then when we come to the second loop, we'll check if it is empty. No. Then what will be our size? 3. So we can remove 3 elements from the queue, add their children, and at the end of this operation, what will be remaining on the queue? Next layer element. You got the point, huh? We can do one operation. Let's say there is a child here. Size will be 3. We'll remove 3 elements. 2 will be removed. 5 will be inserted. 3 will be removed. 6 and 7 will be inserted. And we have removed 2 elements. There is 1 element remaining. We'll remove 4 and we'll insert it. So 4 loopings. Now we can see that these elements belong to the third layer. You see the logic behind using for loop? We can use a pair or something to keep track of their level alongside themselves when we are inserting to view. But this one will decrease the space complexity. On the symptomatically, it will not decrease it. We'll still have a queue with number of. At worst case, if the root node has connection with all the nodes, it will have n elements on the queue. So time complexity, asymptotically, it will not decrease, but practically it will a little bit, and it's more cleaner to use this one. Any question on this approach?
It's an empty graph. Level 1, we want to, int level is equals to 1. When we return the level, it's going to be 1. Or are we going to check the root?
Yeah. Since there is a main function, we can call this main function before calling the BFS, we can handle that. Are we cool? Okay.
Look at the code here. We are this deep in this while loop, right? And if we try to put that line over here, what's gonna happen? It's gonna come over here, right? It's gonna look ugly and like there is higher risk of making a mistake there. And this makes it a lot more easier to understand and readable as well. So that's why when we are writing code, like we should keep in mind that like, how can we make it easy for people who come after us can have good time understanding it. So if we approach this way, this can help us to write such clean and concise code. And this is something that if we start paying attention early, we are gonna get even better in the long run. So that's why I wanted to call this, and thank to Faya for this good organization. And the second thing is, let's take a look at this DFS and BFS code. All right. So in DFS, you can think of, we want to traverse this graph greedily, meaning like whatever comes next, we want to take it. Whatever comes next, we want to take it. This is how we approach to the graph. Like we start from 1 here, and then go to 2, and then 5, and then 9. And if we add more nodes over here, we were gonna go those, right? So this is how DFS approaches things. And as a result, when we want to turn back, we are going to visit the first thing that we just left first. So that's why this is kind of creating a stack behind. Like it's going deeper and deeper and creating a stack behind. Whereas once we take a look at BFS, now let's go to BFS code. Like here, things get done more fairly. What do I mean by that? So first we have to start from some point, right? And it's starting from the root. And we add this guy, and then we start our process. As long as there is an element in our queue that we are going to process, we keep going. And then we get the next element from our queue, and then check if it is leaf over here. And after that, we keep going and then checking if it has a left child and if it has a right child. Actually, this is the part where it adds its children into the queue. And it does them in order. And in the queue, we keep everything in order. So things are done a little bit more like in a fair way. You can think of this way. And when you want to reach to the shortest path, like you want to get things in the best possible way, right? So that's why BFS is actually guaranteeing you that when you reach to some point, it is the shortest path. Because it never did the greedy approach and going things without considering other alternatives. Like it just added everything in the next level first, right? When we get 1 out of the queue, we inserted 2, 3, and 4. And at this point, as you see, all the children, they have the same potential, right? If they have something more promising, shorter to the next node, it can be presented. So this way, with BFS, we can get to any kind of node in the shortest possible way. And I guess we are going to learn more about how to detect which one is BFS, which one is DFS problem from FIRE. Thank you.
Okay. At this point, we can return the level. It doesn't matter what we return here because we'll have at least one leaf in the graph, and this will be the determining factor. Let's see. Yeah, it's working. Let's try to submit it. Much faster, right? I think for easy question on LeetCode, the test cases are a little bit weak, and sometimes you might get better runtime in BFS rather than on DFS rather than BFS. But we don't have to worry about that. We just need the concept and the approach. Which one is faster on which problem and which one is faster on which problem. Any question?
Are there any questions that doesn't matter which option is DFS or DFS or any question as a score one of the questions.
Any question with both of them the same? Any question with when we apply both of them, it will be the same. The time complexity, all the practical.
Coming around every question, if we encounter some question, you can do it either way. There's no
Yeah, there are some questions that you can solve in both and they don't have any effect. Let's say we can simply take the example of printing elements on a tree. Whether you use a BFS or DFS, will it matter? There are certain questions that are like this, in which choosing one of them will not matter. You can go either way. Sometimes, personally, or if the question can be done both in BFS and DFS also with no effect, I'll choose DFS because it is simpler and we can use recursion also. So yeah, there are some questions.
I think his question was: is there a kind of questions that can be solved only with BFS or only with DFS?
Only. I don't think, but
I mean, if I encounter some question, I can't figure out which one is the best approach, and I choose random. I'll probably
I think you can solve questions. You use both of them, but depending on the question, one of them will be efficient. I don't think there are questions that you can't solve by one another. I don't know. We can check it yet.
Which one is better in memory space? Yeah, in terms of memory, I think one is better, right?
Yeah, in terms of memory, it depends on the question. But BFS has a little bit more memory. So each time we are going to add children. If the graph is dense and have a lot of connection with the nodes, we'll have a lot of elements on the queue. But if we use DFS, we'll use one class and will revert back. So it will be on Bfs, it will be maximum height of the string or the height, the length. So on some question, Bfs have more complex, more space. Will take more space on a question. Any questions? So let's take it.
Can Bfs implemented using
Recursion. How can you manage levels in recursion? I don't think so. That's the reason we are using Qt. Okay, let's take 5 minutes break and okay.
What if it not as a cycle?
Not as a cycle.
When we have to do things,
Yeah, if there is a cycle, or means on the tree there is no cycle. But on some graphs there might be cycle. So we need to keep track of the visited nodes. If we have seen a node before, we are not going to add it onto the queue. There is a code on the slide. Here, we'll keep track of the visited. It is a set, and we'll add them. And we are going to add neighbors if they are not in the visited set, meaning if we are not discovered it. If there is a cycle or there is a way to go back to nodes that we have visited, we need to keep track of that.